And welcome back to Mechanical Systems Design. In this video, we'll continue discussing mass efficient design with an emphasis on how we can incorporate finite element analysis. So it'll be best if you've already read the topic reading and watched the previous video, because we'll build on them. And today we'll mostly do exercises, so it'll be especially important to have pencil, paper, and a partner to get the most out of the experience. So we'll start with a couple quick exercises looking at stress patterns. And in this first case, here's our scenario. Imagine you're designing a component that will connect some infinite ceiling that you can connect to with magic glue to some force that needs to be applied at a distance below the ceiling. And you've brainstormed a bunch of candidate designs, and one of them is this. It's a cone. And you've done a free body diagram analysis, some back of the envelope analysis of stress, and so on. And you've moved on to some finite element analysis, and you run the FEA, and this is the stress pattern that you find. Now, what I'd like you to do is look at this pattern of stress and think about what it tells you about how you could improve the mass efficiency of your design. And just spend a minute or so thinking about it independently, then discuss with a partner, and then come back. And you can hit pause now. All right, so probably what you noticed is that the stress varies strongly as you move along this component. Up here, it's pretty low, and I haven't given you the scale, but it turns out the stress, the blue color does correspond to a pretty low stress. And at the bottom, it corresponds to, this red corresponds to a much higher stress. And so maybe you thought in a well-designed part, a mass efficient part, the stress should be relatively even. So is there a way we can remove some of this material at the top and thereby get a more even stress distribution? And there are lots of different ways you can do this. And here are a couple examples. So one is to say, all right, the stress is F over A. I want the stress to be uniform. And so I want the cross-sectional area to be uniform. And if I reduce the radius of the top so that matches that at the bottom, I have a rod instead of a cone. And it will turn out that this is a very good approach. Here we see that the pattern of stress is very uniform along the length of this rod. And it's red, and you might first think, oh, that's bad. Red is high stress, but again, we don't have the scale here, and it will turn out that red is some moderate level of stress, and if you pick your radii well, it'll be exactly what you want to achieve your factor of safety. Another approach that we sometimes see, especially among beginning designers, is to say there is material here that has low stress. I'm going to put a hole in that material, and thereby I'll remove material and reduce weight. And that's true, but it also introduces some complexity. You notice that we have stress concentrations on the edge of the hole, and there's some material here that still sees very little stress. And if you compare the two, we actually haven't reduced the mass of our component very much. This is a huge reduction in mass. This is a much smaller percentage reduction in mass. And so the message here is, when you see that there's an opportunity to reduce the material in your component, try to change existing big parameters first before you introduce new features that increase complexity. All right, let's do another one. So in this scenario, imagine that you are designing a thing that connects to a wall, again, you can attach with magic glue, to torque that needs to be applied out here in space. And you've generated a bunch of candidate designs, and here's one. It is a tube with a square cross-section in the thin wall. And you've performed free body diagram analysis, some stress analysis to get the parameters about what you'd like them to be, thrown it into CAD, and run finite element analysis. And this is the pattern of stress that you see. So here again, I'd like you to look at the pattern of stress and think about what it's telling you about how you might change the part geometry to have a more mass efficient design. Work on that independently for a minute or two, then discuss it with your partner for a minute or two, and then come back. And please hit pause now. All right, so presumably what you noticed is, again, we have this uneven pattern of stress, although now the distribution is more complicated. We see that there are these blue regions on the outer corners of the cross-section. And there are much higher stresses along these sharp internal corners and also in the middle of those faces. And perhaps you thought about ways to reduce those stress concentrations and remove some of that outer material. And there are a few different ways you could go about this, but most of them lead you in this direction towards a circular tube. So there are a couple ways I can imagine getting here. One is you say, oh, those corners are bad. They're leading to inefficiency. So is there a shape kind of like this, but that doesn't have corners? Ah, a circle. Okay, circular cross-section. Good. Another way you might work towards it more step by step is to say, okay, I'm getting these concentrations on these internal corners. Let's add a fillet. And then I have this unused material on the outer corner. Let's fillet that as well. And then you rerun the simulation and you'll see that made it better, but we've still got this uneven distribution. As you increase the radius of the fillet, eventually you get a circle. And so that's another way to walk up to this. And I should mention that here we have the scale to show you that even though the inside is blue and the outside is red, the difference in the stress is very small. It's true that the outer stress is a little higher because tau equals TR divided by J, and the radius, at the distance from the centroid, is a little bit bigger on the outer surface than on the inner surface, but it's very minor. And so the message here is, sometimes when you see an uneven pattern of stress, it's a good idea to try a qualitatively different but equally simple shape. All right, so now we're going to do a little bit longer example where we'll also use those patterns of stress to improve our models and our design. And here's the scenario. So let's say we have this ground surface we can attach to, again, with magic glue. And there's some location in space above the ground where we need to apply a force upwards and a moment clockwise. And we brainstormed a bunch of designs to try to connect this point to the ground with as little mass as possible while maintaining our factor of safety. And one of our candidate shapes looks like this. And then we've done a free body diagram of this part. And here's the FBD that we've generated. And we see that we've got a force downwards at the bottom that is equal and opposite and collinear with the force upwards at the top, and an equal and opposite moment at the bottom. And we've done our static equilibrium check, works out. Deformation seems okay. So we've taken it to CAD to run an FEA sketch. And in this case, we're going to model this rather than having one hole with a big moment on it. We're going to model this. You get the same effect by having an upwards force that's bigger than a downwards force that's offset from the first one. Okay, so we've run our finite element analysis, and this is the pattern of stress that we see. And the question I'd like you to try to answer here is, why do we get this pattern of stress? And I want you not to focus, there's some complicated stuff happening up here around the holes and these corners and stuff, but I want you not to focus on that, but rather focus on the stress in the bulk of the material, which is down here. And to make it a little easier to see that, we're going to set the red limit to a lower value so the pattern becomes more evident. So try to answer the question, why do we have this pattern of stress? And use concepts and language from solid mechanics, stress analysis, and statics, free body diagrams. Work on that a couple minutes by yourself, and then discuss it with a partner for a few minutes, and then come back. And you should hit pause now. All right, so what you've noticed is that the pattern of stress is uneven. It is not uniform across the cross-section, as we would expect from pure tension, say, and it's not high on the outer edges and low or zero in the middle, as we would expect from pure bending. Instead, it's high on this edge and it goes towards zero or something low on the other edge. And that's because we don't have pure tension or bending. We have this couple. We have combined loading, and therefore we're going to get this combined stress pattern. And what's happening is, if you think about those diagrams you saw in solid mechanics, you've got this axial pattern of stress, which is nice and even across the cross section. And you've got this bending pattern, which strongly varies across the cross section. And then you add them together. And on this side, we've got tension adding to tension, and we get more tension, so bigger stress. On this side, we have tension that's adding to compression, and they cancel each other out, and we're getting low stress. That makes sense? Okay. So now I want to take a look at this pattern of stress that we understand we're seeing, this combined stress pattern, and the pattern that we see in FEA, and challenge ourselves to take this to the next level. Is there a simpler free body diagram we could draw for this component than our original one that would possibly more simply capture our understanding of the loading? And that might lead us to improved designs. So take a moment and see if you can draw a new, different free body diagram that is consistent with these results. And spend a minute or two working on that individually, then a minute or two discussing with your partner, and then come back. So hit pause now. All right, so the trick here is to recognize that for static equilibrium purposes, you don't need to know everything about the stress distribution. It's sufficient to know what the integral is, that gives you the total force, and where the center of pressure is. And we'll get an equivalent statics result if we apply that force at the center of pressure. And so something like this is a good free body diagram for this component as well. And you can see that we have these two forces still. We need those forces to get force balance in the vertical direction. But now, instead of getting moment balance by applying a moment down here, we're saying we've offset this force. So F times D is our moment from that offset force. And to get moment balance about any point, but we'll pick this one for convenience, we need M to equal F times D so that they cancel each other perfectly. And that means that if this displacement here to that center of pressure, D, is equal to the moment divided by the force, then we'll have static equilibrium. All right, so now that we've got these stress results and this new free body diagram, does this suggest to us a different shape that might be better, more mass efficient in this scenario? So I'd like you to reflect on these results and generate some new candidate designs. You can generate, 5 or 10 new designs and then think about which ones you like best. Discuss those with a partner for a couple minutes and then come back. So hit pause now. All right, so one thing you might notice here is that if we only need to apply this force over here, maybe I don't need all of this contact with the ground. And similarly, in our FEA result, there's a lot of unstressed material over here. Maybe I don't need that. So one way to adjust the shape to reflect those ideas is to make it look something like this, where we just contact the ground over here, and that's where the force is applied. We make sure that that distance equals what it needs to equal in order to get the moment that's required. And then we just kind of reach up to the top there. Now, there are some little subtle choices here that might not be totally obvious at first, but might also make sense. So for example, if we look at this contact here, it's not zero, it's not a point. There's some finite area, and it has a width A here. And this width up here is a little bigger, B. So what I'd like you to do now is think about what your approach would be to try to select values of A and B. Should B be bigger than A, and how would you pick them? And you don't have to actually go through the process, but I'd like you to think about what would your approach be to identifying the right values for those parameters. And think about that individually for a couple minutes, then discuss it with your partner for a couple minutes, and then come back. And you can hit pause now. All right, so when I ask you what should the numerical value be for some parameters, the first thing you should think of is inverse analysis. So in this case, we're going to think about what is the stress model down here, what's the stress model up here, and then plug in what we want the stress to be, the strength divided by the factor of safety, and then solve for this parameter A or B to figure out exactly what it should be. And if we do that, well, one thing we'll notice is that this is going to be based on simple tensile stress. There's no moment down here, so it'll just be F over A. And up here, we'll have either combined, or if we want to say that the bending dominates, simply a cross-section that's set by the bending stress model. And because we have combined or bending stress, this cross-section will end up needing to be a little bigger. So if we take those values and plug them into our CAD model and then rerun finite element analysis, this is the result we get. And we can see that now we have a much more even distribution of stress along these surfaces, and there's much less unstressed material in the component. There's still a little bit in the middle here, and we could think about ways to address that. For example, making this have an I-beam cross-section, or 3D printing it and making the top and bottom kind of thin and the walls thick. But this has made a big improvement. If we compare it back to our original design, we've reduced the mass by more than half. So by updating our simple models based on the results from finite element analysis, that leads to better understanding of our design space, which leads to better guesses, and that can greatly improve performance. Now, some of you might be looking at this design and thinking, that doesn't make any sense. You know, that's going to break if it gets a different kind of load. And that's true. So this kind of design does make sense if we know exactly what kind of loading it will experience. And if you look inside a machine, you'll see lots of parts that look kind of like this, where because it's inside of a system, we know exactly what type of loading it will experience, and we can optimize for that. If instead there are a bunch of different types of loading that we expect it might experience, we should model those and then understand what shapes would be good to prevent failure in those cases, and then make one part that incorporates all of those features. And that generally results in a less specialized optimal shape, but still an optimal shape. All right, our next exercise, we're going to try to catch an error. So here's the scenario. You are designing a component that can connect to a wall at the top and the bottom, and you have this clip component that needs to be supported. And it's got a square peg and this force from a rope that will pull down hard. And you've generated a bunch of candidate designs. This is one of them. And you've done some hand analysis and plugged it in to CAD and run FEA, and this is the result you've gotten. And there is something wrong, and it's a big problem. It's not just a little detail. So what I want you to do is now look at what we've got here and see if you can figure out what the problem is. Do that independently, then discuss it with a partner, and then come back. It should take about 4 minutes in total, and you can hit pause now. All right, so maybe you noticed that the applied force here is just normal to that surface. And you can see that's consistent with the arrows that you see and with the pattern of stress here. This bottom part seems like it's mostly in compression. Well, that implies this free body diagram where you have a downwards force on the inside of that square hole and some upward forces at the bottom and top. Maybe the bottom's a little higher, and you can see because it's stiffer connection between the surface and the bottom. The problem is that if we now do a free body diagram of the clip, we see that, okay, we've got this upward force from contact with that surface. We've got this downward force from the rope. Those things would cause a moment, and this thing would tend to spin unless we have some kind of reaction moment at that interface as well. And maybe the way that really happens is that this force is actually located at this corner, and there's a downward force at this corner or some other more complicated interaction. But the point is that the two FBDs are incompatible. They're inconsistent with each other. And therefore, this free body diagram cannot be an accurate model of the loading of our component. And that has led us to load the component in finite element analysis incorrectly and given us erroneous stress results. If we go back and model it more accurately, we see a pattern of deformation more like this and stress more like this. And the peak stress has increased by about 20-fold. So these little mistakes we might make will really propagate through our computational models. In other words, we can't use finite element analysis correctly if our back of the envelope analysis isn't really good. Okay, in our next exercise, we'll start to look at how we might optimize detailed parameters using finite element analysis. So let's take this scenario. We have a peg that is frozen in space, and then offset from it to downwards is another peg to which a large load will be applied. And we need to make a component that holds these things together. Sounds kind of familiar, although pegs instead of ropes. And we've brainstormed a bunch of different designs, and here's one that we're considering. And so we've got this main section in the middle that's simple axial element under axial tension, and then we have these hoops at the top and the bottom. Now, probably from project one, you'll recall that a good way to select the parameters for this middle section is to use inverse stress analysis to set the cross section. Sigma will equal F over A, where A is the cross-sectional area. And we want sigma to equal the yield strength divided by the factor of safety. So the area should just be the factor of safety times force divided by the yield strength. And if we do that, we will optimize this middle section of the component that comprises most of the mass of our part, and we'll have a pretty darn good design. Regardless of what happens up here, as long as it's sufficiently strong, even if it's a little heavier than necessary, we'll still have overall a pretty darn good design. But let's say we want to really get the details as lightweight as possible. Then we should try to analyze these features as well. So what I'd like you to do now is take a moment and think about what new parameters are introduced by these features and what approach we could use to try to identify the optimal parameters, and then actually try to write down, draw a sketch of your approach and write down a little math, try to get at an answer for what one of those parameter values should be. And you can pause now. All right, so what we've added here is some geometry around those pegs. And a really simple way of capturing that would be to say it's just a hoop around the peg that has constant width and thickness. So we'd have two new parameters to try to solve for. And a really, really simple FBD that achieves static equilibrium would be to say there's an upward force in the center of the soup and then 1/2 force downwards on either side. And that would achieve static equilibrium. And that would result in, say, a very nice even pattern of stress across this cross section equal to 1/2 the force divided by the width times the thickness. But this is a little bit optimistic, but it could probably still get us in the right neighborhood for values of width, say if our thickness was already selected for based on the main portion of the body. Let's throw it into FEA and see what we get. And you can see right away that, yes, our guess is a little bit on the optimistic side. The pattern of stress across this section is not even. It's pretty low on the outside, and it's pretty high on that inside edge. So we are getting some bending, and that's having a significant effect on the stress. So we could try to capture that in a slightly better mathematical model, which might inform our intuition and result in better design. So if we return to our model, all right, so what we've added here is the material around this peg. And a simple way to try to capture it is to say, oh, we've got this arc over the top of the peg that has uniform width and thickness. And then we could say, well, a really simple free body diagram that could be used to get a stress answer would be to say all the forces centered in the middle, and then there's 1/2 of the force downwards evenly distributed on both sides. And that would give us a stress of F over A, where F is 1/2 of that applied force divided by the width times the thickness. And we know this is optimistic, right? Because pure axial stress gives us this nice even distribution. That's kind of the best case, but it still might be enough for us to make some pretty good decisions about what the width or thickness should be in order to get something near our factor of safety. So let's say we take this initial guess and we plug it in to CAD and run FEA, and we get this result. So we can see probably pretty quickly that it's not consistent with our and analysis. And so what I'd like you to do now is just try to explain in solid mechanics and statics terms why it doesn't match, what the pattern of stress does imply, and how we might capture that in a simple model. You don't have to write any math, just verbally express it. And think about that independently, then discuss it with your partner and come back, and you can hit pause now. All right, so what we see is we have the stress is varying across the cross-section, and that means there must be some bending happening. Yeah, but the stress is not lowest in the middle, and that means there's substantial combined loading. And this is very similar to what we saw in a previous example, where we have tensile stress from bending over here and a tensile stress from the axial loading, and they're adding together, we're getting a higher stress. And on this side, we're getting a compressive component from the bending. It's canceling with the axial tension. And so we have this high stress on the inner edge and a low stress on the outer surface. So how can we try to capture that in a simple model? Well, we're going to need to have bending in our FBD. So here's one way to do it. Let's say we divide this into quadrants instead of the whole half section, and say there's a force upwards of 1/2 F at the top. Well, now we need a moment at the bottom to cancel it. And in order to get static equilibrium, we need this moment to be 1/2 F times 1/2 D, where that's the distance from the center of the hole to the center of that arc. And if we plug that into our sigma equals my over I equation to get the stress due to bending and plug and chug, we're going to get sigma B equals 3/2 FD over TA squared. Okay, now if this achieves static equilibrium, but recalling the previous image, it looked like maybe there was some bending at the top. And if we do our deformation analysis, this FBD means it would kind of go like that, which isn't what's really going to happen. Like this at the top, that slope has to match on both sides. So another way of guessing at it would be to say, okay, maybe there's also a moment at the top surface. And just to make it analyzable, let's say the moment at the top and bottom surface were the same. Well, then they'd each be half the value that we calculated a moment ago, leading to the bending stress being 3/4 FD over TA squared. And if we then combine those stresses, the tensile and bending stresses, we'd have something like this, where you've got that bending stress, the axial tensile stress, they're adding together, and that peak value would be something like 3/4 FD over TA squared plus F over 2T. So you can see that if we really deeply contemplate the finite element analysis results, that will allow us to improve our simple models, which will allow us to perform analytical optimization. We could solve for A or T in this case. But perhaps more importantly, this process improves our intuition. So we understand why we're seeing these patterns of stress and what phenomena underlie them. And that will make us much better at tuning the qualitative shape or the parameter values as we improve our design and make it more mass efficient. So that's several ways that we can use finite element analysis in a mass efficient design process.